Welcome, everyone. Thank you for choosing this talk. The title is So You Think You Know How to Work with Concepts. My name is Andrzej Krzemieński. I work for Sabre Polska. I also maintain a couple of small open source libraries. We have seen already a couple of good talks about concepts this year. So I hope I will be able to talk about concepts from a slightly different angle. I want to show you a perspective of a generic library author whose primary goal is to deliver a good library to the users and a good experience to the users. And we'll see how concepts in C++20 help with this task and maybe primarily how they don't help. And what traps we can fall into when we trust them too much. So in order to give you the touch and feel of a library author at work, this is going to be a live coding session where you will see me type some code, make mistakes, and then try to fix them. First, we have to say something about the generic programming, because when we use word concepts in the context of C++, we can actually mean two things that are quite different. One is in the context of generic programming, which doesn't really require much from language support. Generic programming is something that we've been doing for decades now, and we used concepts there. And there was no direct language support for concept. We would just have to read the documentation like the one that SGI used to offer that would describe all the things that your type needs to do. You would get a list of associated types that it is supposed to have, operations that it should provide. And once you learned all of this, you would be able to use the generic libraries correctly. So the concepts would be like interfaces in generic programming. And the other word, the other definition or use of the word concept is a concept slide feature that was added in C++20, whose goal is to help with generic programming concepts to reflect them as much as it is possible. But it is possible only to a certain extent. And there are limitations that we are about to explore. Maybe one thing we should still mention before we go to our adventure, that not every template library is a generic library. Like, I maintain a Boost optional library, which was created by Fernando Cauciolo. And it is a template library. So you have to give me some T in order to get optional T, and you can use it. But I do not expect anything particular of your T. I only expect that it's destructible, but it's a very small requirement. So not perhaps not worth mentioning because usually types are destructible. Other than that, you don't have to provide nothing, and you can construct optional objects. But it will not work if you try to do complicated operations. If you want to copy optional T, your T has to be copyable. You want to compare equality with equality to optional T's, your T has to be comparable as well. So it's whatever you give me, I give it back. And this is why it is not a generic library. There is no requirement that I put on you. It's just you get whatever you give me. In contrast to that, I also maintain another library, which is called Markable, which is supposed to address the same problem, but in a different way, of representing the values that are possibly missing. At this time, it is more compact. So if you want to store an optional int, and you can spare some value like -1, I can store it, the flag inside the inside your T, like inside your int, but you have to teach my library how to actually recognize the special value. And for this, you have to pass me a policy. Policy is something that I always require that has a way to set this special marked value and to check whether the special value is here. And now here we have a requirements on a policy type. It always, whatever type you want to store, the policy always has to have the same interface. This interface is a concept. And this is what makes this library generic. And of course, my real concept when I try to conceptualize it in C++20 is far more sophisticated because real life concepts are rather big. So, okay, let's start with the library. We'll use Compiler Explorer, GCC 10.3, which implements concepts light in C++20. And we will pretend that we are writing a library lib, which has a very clever algorithm. Sum, it will represent an algorithm in a generic library. And if you provide operator plus, I know how to implement my algorithm sum. Sorry for a silly example, but we have to fit into 90 minutes presentation. So it will be big enough to take all our time. This is a generic library that I want to use for users. And at some point, I decide to add a concept to express my requirements. I add a concept addable. If you heard and attended Jeff's talk on Tuesday, he says that the concept like addable is probably a code smell. But again, first, forgive me, but I have to fit it into 90 minutes presentation. And second, the point of this talk is to show you how we can do some silly things and then perhaps correct them. So actually, it's my point that it may be too small. But I assume that you already are familiar with concepts, like at least superficially. So you should know what it does. I will only make a very brief introduction. A concept is a template. So we already have like 4 categories of templates: class templates, function templates, variable templates, alias templates. And this adds to the collection. We have a 5th, a concept. So it is parameterized by some types. And I'm actually defining a predicate, compile time predicate. So it's almost like a variable concept of type bool. I'm composing it of other concepts. So I say I defer my definition to another concept from a standard library, which is called regular. We'll probably find it in the list of concepts that there is something like this. And it requires that the type is copyable, movable, assignable, default constructible, or all this regular stuff that we have. And now I use this ampersand, which, although visually close, it is not a logical end operator. It is a conjunction operator in the concepts world. And it has some different properties like compile time short circuiting and some other clever stuff. And then I use requires expression to express my further requirements. And in this case, I say I will be using names O, A, B of type T, and what expressions I require of them. So it has to have operator plus that works on 2 T's, and it should return something specific constrained by another concept. Stud convertible 2 is another standard library concept. We can find it somewhere here. This is a concept, again, a template that takes 2 parameters, from and to. But I listed only one here. This is one magical property of the concepts that are, at least in this context, that I can not type or skip. In fact, I have to skip the first parameter, and the first parameter will be deduced from this expression as a return type of this expression and passed by the compiler here. I will only provide the second concept, and as we said, the concepts are predicates, so it will evaluate the predicate and will check if whatever this plus operator results is convertible to T. This is a new syntax, even though it may look familiar. It requires expression comes with its own syntax that we have to learn. For instance, nowhere in normal code can you put an expression inside braces without a semicolon. Here you have to. So it is a different syntax that we have to learn, and it is easy to make mistakes here. For instance, I could rewrite my concept like this. And it would look like it says the same. I want regular and want plus and plus equals. It would compile and it would return true for regular types, but it would also return true for irregular types, because this actually checks whether I can ask if my T is regular, but I'm not interested in the answer. If I want to also check if this predicate regular returns true, I would have to type requires. So there's a new category of bugs that we can plant when specifying the requirements on our types. But let's go back to our previous implementation. We have another requirement that there is plus equals operators. And now I'm using another standard library concept, same as. Again, this has two parameters and returns true if the two parameters are the same. That is, the same is what this operator returns and what I type here. So I'm, in other words, I'm saying that the return type must be exactly T reference. And now I want to constrain my library with this concept. And why do I want to do it? Because apparently my users already use my generic library and it works. So the goal is to give my users better experience when something goes wrong, when they make a mistake, pass me the wrong type. I can already, with some amount of compiler finite tricks, check for things. But if it's concepts, this is something that my users will go to and be able to read, because now it's a declaration, so they will be able to read it. They will perhaps learn for the first time that there exist things like concepts, and the communication will be easier. We said that, one thing that they didn't have before, they can just evaluate my concept without invoking any algorithms, because a concept is a predicate. So what they can type is main will be representing our users here in this example. Static assert. We'll check if int is addable, compile this program. It didn't fail to compile, so the user confirmed that that int is an addable type. We have a question. Why can't I just type 0 plus b like here, just returns t? Because this syntax just doesn't work. If we try to do this, we get a compiler error that this doesn't work. You could say, so why does it not work? And this is because there would be different expectations of this syntax. should this mean that the return type should be exactly t-reference, or is it enough that it is convertible to t-reference? What about the expression templates that sometimes are used for matrix libraries? When my plus operator actually returns something, just a reference to the operands, and which is a different type, and only at the end builds the next t. So it would confuse some people. So this way we force you to be more explicit, but as you can see in this example, you send a clear message whether you mean that it's enough if it is convertible to this type versus if it's identical. So I'm not sure if this fully answers your question. The short answer is because you cannot use it like this. So yeah, there is a comment that at some point it was a legal syntax, and in slides of other presentations you will still see this used, but this no longer compiles. And it used to mean something convertible to t, not necessarily t. Okay, moving on. So we've seen it is a predicate, and now I'm going to constrain my algorithm with this concept. And what we often hear is, this is in order to make the error messages shorter. So let's check if this is true. First, let's start with unconstrained template. We'll create some struct that doesn't have operator plus at all. And we'll try to call our function sum. Let's compile. This is the error message. It's quite informative. This is a plus b that cannot work when I call function libsum. Now let's constrain our template. There's two ways to do it. One is longer. We use the requires clause. Requires. It expects a Boolean predicate, so we say that concept addable when passed this argument t should return true. But another way to do this, a shorter one, and this is the specialty of concepts, is that we can put them inside the template declaration. And this time we can skip the first parameter like we did here. We also skip the first parameter, but if we are left without any parameters, we can as well skip the angle brackets, and we end up with this addable t. Now let's try to compile our program. Definitely not shorter, but way longer. And not only longer, because now I am also, or my users are also exposed to some names that they cannot see here in the concept that start with 2 underscores, which means it is an implementation detail. So I actually made it worse. Now you can see the implementation details. Where do they come from? It's this concept regular, because the concept regular, if we go to the documentation, is required to be composed of further concepts like semi-regular and equality comparable. If we go to equality comparable, it is required to be an alias of some implementation defined other concept. In the requires, it is required to, in the requires expression, it's required to be constrained by another implementation defined concept. And it is all requirements that the implementers of the standard library must provide in order to make the overloading based on concept, which is a very fragile process, work correctly. So even though if we cannot see it, this is not the implementation details of my algorithm, but this is implementation details of concepts. So even a concept has a lot of implementation details inside, and now my users are exposed to this. But the example is nasty. It only proves my point. In other cases, it would be the inverse. And I still get something from this transition to concepts, because all this error message only talks about the concept, only about the interface. Yeah, there is no error or line here that points to the guts of my implementation. So we shifted the details of the error from my implementation to the interface, however big it seems. Okay, but now let's do something interesting. Suppose that in my library, I know how to implement function sum more efficiently. I discover that at least for some types, the implementation is faster if instead of operator plus, I use operator plus equals and make sure that the bigger operand is on the left-hand side. Of course, it's not true in real life, but let's assume this for the sake of this presentation. So I will go with some implementation details. Conventionally, when in header-only libraries, when we put some implementation details, they need to go in a header. So we use namespace detail to tell to the users that they shouldn't look inside. It is just that we don't know how to do it, or it is not. We didn't know how to do it before modules. Namespace detail says that this is implementation details. And there I will have function sum with underscore, which is another signal that this is an implementation detail. We make sure that A is bigger or at least equal than B. And we return A plus equals B. And in the implementation, we first check if A happens to be smaller than B. And if so, we invert the order of arguments. Oh, I missed the return statement. Otherwise, we just return we just pass the arguments in the normal order. And another observation here is that while I constrain this concept, this algorithm with my concept, I don't constrain this one. And this is a reasonable strategy because concept is an interface between me and my users. And here, this is an implementation detail. So I do not have to interface with myself. And a user might want to check if the type like int is addable. You may try to add two integers, 1 and 2. You can use another feature from C++20 concepts that it's not just auto, it's auto constrained by a concept. So it means, yeah, I'm deducing the type from the initializer, and then I make a static assert if what I deduced is constrained by this concept. And then let's print the result out. Yeah, and it outputs 3. So it works as we expected. But in order to be sure, let's test it with other types like double, 1.5, and 2.0. Now we expect 3.5 in return. We do, but this is our scalar type. So let's test it with something more serious, some other library. Let's try Boost Rational. Rational numbers. This is the template, so to make it short, Boost Rational. We have to specify the types of the numerator and denominator. It will be int. We check if this is addable first. Let's compile. Now it takes longer because yes, it compiled fine. So it means that Boost Rational is actually an addable type. And let's try to create two variables. We have a question here. How about if we pass string? We'll get to that. But now let's do it for simple enough types. And create two variables. Sorry, I forgot where I was. User TA, which will be 1/2. B will be 1/3. So when we sum them up, we expect it to be 5/6. Compiling. Yeah, 5/6. Let's just give it one other shot with Boost multi-precision library. This is for storing those big ints that we have to allocate memory for. Multi-precision CppInt. This is the default implementation of the big int. This time it's not a template. CppInt. Now we use strings to initialize them to 233. So if we sum them up, we expect 3355. Let's check if it compiles. Still compiles. Yeah, 3355. So it works. We've tested it on a reasonable number of types. We get some confidence. We're never 100% sure if it works correctly. We can ship the library. And now our user decides to use it with type complex. Let's first check. This is a template again. Of course, this will not compile. First, the user checks if their type is even addable. It is. It compiles fine. So let's create two of those. No real part and imaginary part is 1. For the other one, the real part is 1, imaginary part is 0. We expect 1 and 1. Let's compile. And we get this error. Because even though we didn't say it in our requirements, we use operator less than in our implementation. And now, even though we have a concept, our user sees the guts of our implementation. And here we arrive at the first gotcha with concept slide. Let's go to maybe my slides. The fact that you constrain your algorithm with a concept doesn't mean that the compiler will check that in the implementation, you will only use the interface that you have declared. You have no such guarantee. in C++11 concepts that never made it, this was actually checked, but not here. And on the other side of the interface, from the user perspective, when you test if your type satisfies the concept and you get a compiler failure, yeah, then this is a guarantee that your type will not work with my algorithm. But if the check like this returns true, it is no guarantee that your type will work with my algorithm. And this negative guarantee doesn't seem like a lot, but actually it already gives us a very useful value, because it protects us against users' types accidentally satisfying our requirements. What I mean by this is that it's possible that I have a function differ like here that uses operator equals to check for inequality, and it works for some user types that don't have operator bang equals. But if I at some point observe that bang equals is actually a better implementation of my function and I change it, I would potentially break my user's code. But now if in my interface I require more than I need today, I protect my interface for the future implementation. Yeah, I give myself a freedom to change the implementation if I require too much. This is what concepts in the language give me. Okay, but we did some testing. Sorry for that. We did some testing in order to protect against it, and it didn't work. And why? And this is because we tested on real practical types. And this was our mistake. Well, you should test this as well this way. But those practical types, those real libraries, offer rich interfaces. And what we missed here is actually some narrow interface that would only use the operations that we need and nothing more. And it is likely that for concepts that we define, we will never find them. So we have to write them in order to do a decent test of our library. We have to write them ourselves. We will create something that is called a concept archetype that C++11 concepts actually had automatically. We'll look at our concept and we'll create a type that satisfies the concept and does nothing else. That will have the very minimum interface. And then when we have it, we will test our implementation of the algorithm with this concept archetype. So let's do it. It will be our implementation detail. Our users will not know that we are testing our types. It will be a class A. We will start with an empty interface, which of course doesn't work, and then we'll expand it until we satisfy all the requirements. We'll check it with static assert. Maybe we'll give it a better name. Addable archetype. And we'll check if addable is satisfied by this archetype. And the thing is that if we only use braces here, open brace, close brace for a class, it doesn't have empty interface. It already comes with default constructor, copy constructor, the big five, the assignment operators. So in order to start from an empty class, we would have to delete all of those, or declare as deleted. And given the rules for which member functions, which of those magical functions are automatically generated, we know, or we should know, that if we declare the move constructor as deleted, all the big five becomes deleted. We have no default constructor, no copy constructor, no move or copy assignments. And there are other functions that we get by default, which we also don't want. It is a comma operator and address of operator. So let's remove them as well. Address of and comma of 2 A's. Okay, but in our type, we actually require all those default constructors, move constructors, move assignments. So let's add them back. And this should satisfy the regular concept. And now operator plus and plus equals. A reference plus equals. No, we don't have to implement it. It's enough that we declare it. And operator plus. It has to return A. And it takes 2 A's. And let's check if we have implemented our, no, we haven't, because I forgot to return something here. We can now also comment out the previous error, which obviously will not work now. Well, that one will work actually. And check it. And we have still assertion failure in line 26. Yes, because we forgot about copying comparison operators, because regular is also comparable with equality and inequality. So let's add it. And in C++20, we can do it with one instruction, with one declaration. And bool op. Default. And it also generates operator bang equals for us. So now we should be good. Yeah. So we declared something that satisfies our concept, but we failed to meet the other requirement that it should be minimal, because minimally we require that A plus B returns something that is only convertible to T and is not necessarily T. So we need to do something smaller here in order to be really minimal. We will define a private nested class. Let's call it result. Or maybe make it public interface, whose only meaningful operation will be conversion to A. And it should not have anything else, so we have to repeat the exercise. No regular interface. I will now risk doing a copy and paste in order to delete the other two operators. Now, of course, it may work, but it's not the point. We actually have to use it. Let's check it. Yeah, now it's fairly minimum. Of course, if we look closely, it's still not minimal because, for instance, I don't require that the operands to the operator plus are really t's. It's enough that it is something that I convert from t. But at some point, I have to stop here. Like I have to draw the line between how much value I get from this exercise versus how much things I have to type. And as you can see now, this becomes more complex than my actual concept. So I'm good with this. And now to write a real test. Again, it will be an implementation detail. So let's go with namespace detail. We will use some function for testing. And the test is to actually instantiate my algorithm with this archetype. Let's call it test sum. And we will call sum with double t something. And yeah, we expect that to compile, but there is something wrong here. It will work for our concept addable, but in general, because our concept addable is default constructible, but other concepts in there may not require default constructibility. So we wouldn't be able to construct our archetypes like this. In fact, there may be concepts that don't require constructibility at all. It doesn't mean that the types they constrain are not constructible. It only means that the algorithms that rely on this concept are not allowed to create objects of this type. So in order to handle these cases as well, we would have to do another trick. And this will be to do the same as we do in the requires expression. Just introduce artificial variable names that we will never initialize. Let's do it here. Now we will never call this function actually. This function is just to be there, to be compiled, and it will trigger the instantiation of our algorithm. But no one will ever call it. So no one will ever initialize those parameters. So we don't really need any construction here. And we can additionally test if the result type is addable. Let's run our test, that is compile the code. Again, we can see the same error, but this time this error comes from our test. So we detect our bug, not our customers. And now we detected the bug, but it is not clear how we want to solve it. We have to make a decision. Apparently, we use more operations than we require in the interface. But is it a bad interface or a bad implementation? We have to make our call here. The compiler will not help. Maybe we should accept that we'll be rejecting types like complex, because they don't fit into our abstraction. But maybe our library used to work before with this type. So maybe we should abandon the idea that we will provide a faster implementation in order to facilitate just any type. And the third option would be to provide two overloads. for our function. One that works just for any type, and the other one that works for those types that additionally provide operator less than, and similar. But we don't even have to do that, because another thing that we can do is to use if context per. We can if context per. We can ask at compile time if our type T is additionally totally ordered. And if it is, then we will go with this implementation. Totally ordered is another standard library concept. Oh, sorry. Which requires the additional, we can see it here directly, which requires the additional comparisons. So where are we here? Otherwise, we'll go with the default implementation. Let's just return A plus B. Yeah, and now everything works. Our type can be used with complex number. Let's confirm it. Yeah. So although we were never taught that, if context actually blends or seems to blend with concepts. So the question is, should I do this if context per trick, or go with two overloads? And the answer is, to a great extent, this doesn't matter. There is a tiny little case where possibly it could matter in the future, but they are more or less equivalent, except that, as we will see later in the talk, switching from one implementation, from one algorithm to another, cannot ever be a implementation detail. It is something that we have to communicate explicitly to our clients. So if we do an if context, it goes inside the implementation. Our users will not see that we are providing two implementations, and this may sometimes cause them a lot of trouble. So if we choose to go with if context, we have to provide other means of communicating to the programmer that we are actually delegating to two implementations. So we will not do it. We will go with two overloads. There's something on the chat. I got +1 for if context, but now I'm saying I don't recommend it, so I don't know. I hope that you will see towards the end of this talk why if context is not a good solution here, if time permits, because I see we are running out of time. So we will go with two overloads. And this is another feature offered by the concepts, that we can have two overloads that do not differ by the arguments or return type, but they differ by constraints. And the other one will have a more complicated implementation. And we will additionally say, we'll use the requires clause and say that we require total order. It should still work. It works. We cannot see it, but I just compiled it. But this is not the end of our possibilities, because another thing that we could do is, rather than putting this requires clause, is to introduce another concept. Ordered addable. It is not difficult to actually write it. Concept, ordered, addable, is addable, and is totally ordered. Let's see if it compiles, if I didn't make some mistake. Yeah, it still compiles. So which one should we choose? Just to go with totally ordered here, or to introduce another concept here? And in fact, as it should become clear towards the end of this talk, this is actually the only option. Using the other with just requires totally ordered is not an option if we want our library to be correct. But for now, you have to trust me with this. But we are no longer actually testing our implementation, because our archetype is the minimum requirements. So if we try to call function sum, we will only call this basic overload, and the test will never detect if by accident we use some operations on T that don't belong to the required interface. It may compile still for some types like int, because the ints do have this operator. But we are left with untested one of the overloads. So let's test it also. We have two overloads. Let's create two archetypes, one for each overload, or one for each concept that we provide. So again, in order to make it quick, I will risk doing copy and paste. So it's the same, except that it's in a different namespace. And the only thing I will change here is not operator equals, because we need all the operators here. So we will change it. We'll use another feature from C++20, which is spaceship operator. And with one declaration, we can actually provide 6 operators. I think that's it. And now we should do the same here. Ordered addable archetype. And let's check if this is really an archetype. Compiling, yes, it is. And now let's run another test, another compile time test, and it is quite easy. We just provide another overload for ordered addable. It's within the screen. And yes, now our second test detected that we are using an illegal operation, unannounced operation. So we can fix our implementation, and now everything, should work, even for type complex double. And our library has been much improved. Now we can ship version 2.1 and be confident that this works. Some additional comments here that I am lucky that my concept constrains only one type, but in general, you can imagine that there is a concept that constrains 3 types at once, like predicated iteration. Could put some common constraints on the combinations of iterators, sentinels, which is end iterators, and predicates. And if we have this and want to provide archetypes, we would have to provide archetype for each of those 3 types. So we would have 3 archetypes. If, like in our case, now we have 2 concepts, each constraining 2 types, for instance, we may end up with up to 4 archetypes. So archetypes, of course, are sort of a Cartesian product here of how many types we have in our concepts and the number of concepts. So now back to the question we have. What about stud strings? So suppose, our user observes that plus and plus equals is something offered by strings and wants to use our clever sum algorithm with their string. Let's check, because this is what you should do actually at first. This is what the concepts give you. You can test if your type works with my library. You cannot define them like this. So let's comment up and test. No, I didn't want to type complex of string. I just wanted to type string, sorry. Yeah, it works. So let's create toString. Let's add air and the bus. So you can see I come from aviation industry. Let's add them and test it. And what we get? Buzzer. So not a good solution. And this happens because I did this. I just, even though the user didn't know it, I just inverted the order of arguments in order to make it efficient. And the question is, were I allowed to do it? And the answer is yes. This is what we do all the time. This is what actually concepts are about. Like our concept addable already derives from concept regular. And concept regular is not only about providing copy constructor and providing equality operator. It also requires, even though we cannot spell it out, that when I actually do this copy, it should compare equal to the original. And the algorithms constrained by regular have a liberty to create copies, even if they don't have to, and rely on the fact that this copies equality compares to the original. So regular does these similar assumptions. Same for our addable type. Even though we didn't express it, we obviously assume that A plus B should give the same result as A plus equals B. So we make those semantic, this is actually a semantic requirement that we have. And unfortunately, they cannot be expressed in a concept. But the consequences of not communicating them are dire. Like here, we produced bad results in case of not satisfying standard library semantic requirements. We get undefined behavior. There is no way to communicate them. We could try, like C++11 concepts did provide a feature like axioms for expressing exactly those. We don't have it here. We could try it. And this is actually where concepts as language feature make it more difficult. Because if we didn't have concepts at all, at least users knew that they have to read documentation. And there they would find even the semantic concepts. Now, when we have this language feature, it relieves the user think they are relieved of this responsibility of reading documentation, and they only can look at the declarations in our concept. And there they will not find semantic requirements unless we try to put them in a comment. Or we may try to do some tricks, like I could do this. We've seen on Tuesday talk by Jeff that putting requires is a code smell. But in this case, this is exactly what I want. I want to draw your attention to something special. It doesn't add any value syntactically, because, well, it requires that this expression is valid, but obviously it's valid. I already require plus and equals, so this is nothing new. But because it's so fishy, you may start to suspect that something is going on here. But maybe not. So it's not a perfect solution. And now with maybe we should answer the question: who is responsible here? Because I was allowed to make a semantic assumption like this. Maybe I should have communicated it clearly, but I did it only in the comment. Ultimately, the responsibility for this disaster falls on the user. It is the library user's responsibility to get acquainted with the concepts and make sure that you instantiate my algorithms with types that adhere not only to syntactic requirements, but also the semantic requirements. And you can easily imagine that at some point it will not actually work. We could ask a question: why the same problem does not come up when we are talking about object-oriented interfaces, like from object-oriented paradigms, when we derive from a base class or extend an interface? And the reason it doesn't come up is because of this colon that you can see here. Because when we declare in object-oriented world, when we say that our type implements some interface, we have to say it. There is no other way. We have to say it. Yes, I want my type to implement this interface. And this is actually saying, yes, I got acquainted with the interface, both its syntactic and semantic requirements. And I commit to complying with those semantic requirements. This is what we are missing from concepts and generic programming, because the generic programming works like duck typing. Only because I have these operations, I'm suddenly categorized as complying with the interface, which obviously doesn't work, because the string might not know that there is concept addable. Concept addable may not know that there is something like string. So sooner or later, the disaster will happen. And yeah, and if we don't detect it, we may get into serious problems. So one thing we could do, well, there's a number of things we could do. One would be to use assertions in our code, which would not be that bad if we know. And maybe I should make another point here, which is very important. Concepts always come with semantic requirements. If you see word concept, even there is no way to spell it, it means I have some semantic requirements. We just have to learn what they are. I may not, even the concept author may not be aware of all the semantic requirements that they make. I could try to write a function. No, not type name. Addable T. It probably should go into the detail namespace. That I require, maybe make it, oh, it's inline by default. commutativity. And there would be B, and then I will assert that A plus B equals B plus A. So it will be a no-op in the builds that disable assertions, and it will be an abort, check and abort if we are enabling assertions. But where do I put it? And the only place to put it is in those implementations. This is the only reason why I might consider actually using if context, because then I would have to put my test only in one place. I can tell, and now I have to put in both overloads. I can put it this way. I could also try to check. This doesn't make sense for this particular semantic requirement, but it could make sense for if I had others. If I run this program again, I have some error. 917, of course, requires a semicolon. This is better, except in line. Yeah, sorry for these errors. This is just a namespace problem. Yeah. Now, at least I get a normal assertion failure, which is something which can already help somebody detect bugs. But like this is like any unit test. They may find a bug or they may not. Another thing that we can do is to try to emulate what object-oriented interfaces do and force the users of our concept to explicitly declare that they want to conform. They want their type to conform to our concept. Sorry, or in other words, we can try to turn a semantic requirement into a syntactic requirement. And for this, let's use another template, which will be a variable template. So it's not a function template, not a class template, it's a variable template. We declare a template of bool. A bool value that will be parameterized by our T. Oh, this is what I wanted to see. Enable the bool. There are questions here, so let's have. When I do get the is container that never invalidates the The question is, when do I get the is container that never invalidates iterators on insertion concept? So I think now I'm giving you a hint how this could be implemented. This is the best answer I can give you right now. The other question is, so the axiom keyword is not supported, not even descriptive. Yes, we get no axiom keyword, at least at this time. If we did, it works like comments or like structured comments. You can only declare it, but the compiler will take no action on it. Interestingly, since you mentioned axioms, the axioms were actually declared what code transformations the algorithms are allowed to do. which is the case here also. Okay, but let's move on. We are actually running out of time. We define enable addable variable template, which is actually false. And we additionally require that enable addable of t actually equals true. This is the tricky part, because we could forget to type requires and it would still compile, but it would do something else. And this is also an important part. We put a comment here. Because in modern compilers, when compiler gives you an error that comes from some line in the source code, it will also show you the comment. So we are helping the user understand what is going on. So it is false, and we require that it is true, which means no type in the world will comply with this concept. So if we test it, not even our archetype satisfies our concept now. So for whatever type we want to work with our library, we have to explicitly specialize this template. And look here, not only do I get the error message from the compiler, but also from the library author. And this is something that makes life easier for the users. Okay, so we can enable our addable for types that we know will work fine. So we know that for all the integer scalar types, they work fine. So let's specialize it. We use another standard library concept, integral, which detects all the scalar integral types. You can do the same for all floating point types. There is another standard library concept for that. Point. We have to enable this for our archetypes for sure. But we have to change namespaces, because we have to specialize in the same namespace. And now this is going to be full specializations. And for the other one as well. Let's check it. Yes, it works, because now the error is from the line 137, which is type string. So we got what we want. The type string satisfies all the requirements except this artificial one, which we just added. If the user wants to use a decent type like boost rational, they would have to specialize this trait addable for their types. If they could technically do it for std string as well, but then there will be a lot of places that will warn them that maybe this is not a good idea. Like, for instance, they will have a look at our emulation of axiom keyword here. I could actually wrap it in a macro called axiom, and we would get a similar effect. But maybe it is too tiresome. If this is the only nasty type, because it is a dubious choice to use operator plus for string concatenation. So maybe this is just the only type in the world that that has this problem. And we shouldn't penalize all the other decent users with forcing them to type this enable, specialize this enable if. So what we could actually do is to invert this logic. Rather than saying that enable addable must be true, let's introduce a different one. Disable addable, which is false by default, and we will expect that this does disable addable is false. Of course, the comment needs to change. Well, maybe this comment doesn't make sense anymore. So let's drop it. And this way, we don't have to provide all those specializations here, because now our type works for every type that is not explicitly disabled. We can drop those here. And the only one specialization that we need to add, and we can do it inside our library, is the one for type string. And this is actually template basic string. Now I'm typing class to make it shorter. Character, chart rates, and the allocator. Basic string of character traits allocator. Let's test it. Yeah, and it works again, except that there is less specialization. There's fewer specialization of this template. 1 to 5. Yeah, it's again our string. So we have a choice here. Not sure which one is better, because the enable one is safer, but the disable one is more convenient. In fact, if we look at the standard library, they use the same trick. Like we have two concepts, view and range, which actually differ only that the view should be cheaply copyable and destructible. So it has to have a constant complexity. Complexity requirements is another semantic requirement that we cannot directly express in the const. So if you want your range to be treated as a view, you have to make specialize this enable view. And on the other hand, there's this size range concept, and it requires that it not only that it has function size, but it is an amortized constant type to actually evaluate this size. So this is usually the case, but if your type doesn't, it takes linear time or logarithmic time to compute the size, you have to explicitly disable this concept by specializing this disable sized range. And maybe we have 10 minutes. Let me explain one thing that I said. I said that for those two specializations, you cannot put totally ordered directly, but you have to provide another concept. This is because whether we are aware of this or not, here we make another semantic expectations or requirements. For instance, we may require some interaction, assume some interaction between plus and less than operation. Like if I add a plus b, and I expect that this is less than a plus c, or something like this. And if I have these requirements, semantic ones, and I do, they don't belong to concept addable, because addable doesn't know about operator less than. They don't belong to totally ordered, because it doesn't know about operator plus. They only belong to my new concept. This is why I need a new concept to also describe the interaction between operator less than and operator plus. And in fact, this is a more general observation that when you have a template that takes two arguments, P and R, and P has its own constraints and R has its own constraints, and they are not related, you probably have a bug in your code. This is a code smell, because they should be two functions, actually. A good template in this case will have some gluing concept that will express a combined requirements on P and R. This is in fact what you will see in the standard library, like in function sort. Not only are the individual template arguments constrained, but also you get this sortable, this gluing, with this gluing constraint. Also, if you think of iterators, they also use this trick, although it's spelled differently. No type is an iterator by accident. No, if you put if you add in your type operator star, operator plus plus, it doesn't become an iterator. You have to specialize iterator trace or do a similar trick. There is no way you can make your type an iterator unless somewhere, some way, you type stud iterator. So in fact, this is a fiction that you have, that you get a duck typing kind of concepts. Any real concept will or should force you one way or another to declare explicitly that your type must conform to it. There are some like regular, which is that are so obvious that you don't have to do it. But otherwise, ranges, iterators, they all require your explicit action to treat them as concepts, iterator concepts. So I think that's it. What I had for today, we are getting close to the end. If there are any questions or comments on this, we have a couple of minutes, so we may be able to discuss something here. Maybe one other thing that you observed here in the examples is that I started with some concept, then I had to fix it. And when I fixed it, I had to fix it again because we discovered this semantic requirement. This process will also happen in other libraries. This is a real thing, that it is, again, a fiction that you can first design an interface and then provide implementation for it. Usually it's an iterative process. You refine and make it better. So there is you will hear that the standard library concepts, once they are added, they cannot be changed. It's very unfortunate because, as we've seen with this iterative process, they cannot be right. For sure, we will find some bugs in them. And this is just a sad situation if we really cannot change them. Okay, I wanted to thank everyone for participating and sticking till the end. If there's any other questions or comments on this, this is my email address and my blog address. Maybe you can contact me there. Also, I will try to stick around in this, what is it called? This gather tool. I will go to the library room and you can find me there for the next 30 minutes. If there's something here you would like to discuss further. Otherwise, thank you very much for your participation.